So the keynote topic for our next session is ocean exploration to inform climate solutions and biodiversity conservation. And to explore that topic, we'll be hearing from Dr. Amanda Netburn, who's the Assistant Director for Ocean Science and Technology in the White House Office of Science and Technology Policy. So Amanda got her start at Stanford University and went on to earn her master's degree in Marine Biodiversity and Conservation at Scripps Institution of Oceanography from one of my favorite interdisciplinary graduate programs. Joking aside, I'm honored to say she's an alum of the program I now direct at Scripps, and it's such a pleasure to be with her here today. So Amanda went on to get her PhD in biological oceanography from the Scripps Institution of Oceanography. And since then, she's worked at places like the Blue Ocean Institute and more recently, NOAA. Since 2021, she has been in the White House Office for Ocean Science and Technology, first as an ocean policy analyst, and now as the Assistant Director for Ocean Science and Technology. We're incredibly excited to hear from her today as she talks about ocean exploration, climate solutions, and biodiversity. And with that, I will pass it over to Dr. Netburn. Take it away, Amanda.
Great, thank you so much, Samantha. And just want to thank thanks to Richard, thanks to the Institute of the Americas, and to everybody here for being here for this talk today. I'm really pleased. It's a real honor to be here with this group. Muchas gracias. All right, I'll get started here. Since today is focused on the Pacific Ocean, I thought I would start with this image of the Earth. From this angle, our whole planet is the Pacific Ocean. But really, any which way you look at it, Earth is an ocean planet. The ocean affects everything from the air we breathe. Half of the oxygen in the air is generated by marine algae, to the food we eat. 3 billion people worldwide depend on fish for a significant fraction of their protein and nutrients. The ocean regulates climate by absorbing carbon dioxide and heat from the atmosphere. Understanding how the ocean works, what lives in the ocean, and how all these things are changing is absolutely critical to understanding and responding to our changing climate and natural systems. For example, information on distributions of biodiversity will inform siting and management of marine protected areas. Better understanding of the role of deep sea animals in sequestering carbon on the seabed can guide actions to enhance the role of the ocean in mitigating climate change. Some properties of the ocean that I think are useful to keep in mind as we talk about ocean exploration. First, the ocean is really deep. The average ocean depth is 4 kilometers, and the deepest part of the ocean is 11 kilometers. Scientists typically refer to 200 meters and deeper as the cutoff for deep sea, because there are fairly distinct environmental changes and shifts in species assemblages that take place starting around this approximate depth. Just to set the scene for you, 200 meters and deeper is 93% of all the space on the entire planet that is available for plants and animals to live, and that's land and ocean included. Next, the ocean is really dark. Light is entirely extinguished around 1,000 meters. And yet, almost all animals in this huge, dark habitat are fundamentally dependent on photosynthesis taking place near the surface to derive their food. Except for those that don't, like at chemosynthetic methane seeps and hydrothermal vents, where chemical reactions provide the energy for life. The ocean is cold. The average depth of the ocean is 3 to 4 degrees Celsius, except in some places, in a few places, it gets really, really hot, like at hydrothermal vents, where temperatures can get up over 400 degrees. Despite all these environmental extremes, the ocean is a really fantastic place to live. Of over 30 phyla of animals, all but one are found in the ocean, and more than a third of those are only found in the ocean. These environmental characteristics have led to a unique evolution of a huge range of animals and ecosystems, but it also means it's really hard to observe them in their environment. One of the most basic things we need to study and explore any place, including the ocean, is a map. So I'll apologize that this image shows the wrong ocean for our theme this week, but it does a really nice job illustrating the evolution of maps of the seafloor from the early 1900s to now, from dropping a rope off the side of a ship to modern acoustic methods, and just how much that's helped us understand how the world fundamentally works. As resolution of seafloor maps has improved over the decades, we've discovered the Mid-Atlantic Ridge seafloor spreading, a critical key to developing and substantiating the theory of plate tectonics. Incredibly, we now have the ability to map the ocean floor from space. This image shows satellite-derived bathymetry with resolution on the order of 5 to 10 kilometers, really useful for providing a big picture perspective of the seafloor, but coarse enough to miss some really significant features like seamounts, underwater mountains. This map here is a compilation of seafloor depth data that's been collected with shipboard multi-beam echo sounders. The resolution shown in this map is from 100 to 800 meters, depending on the depth. A massive international effort called Seabed 2030 is now underway to map the entire global ocean to such resolutions, so to fill in all those black spaces on this map. But it's a slow, expensive, and labor-intensive process to do this from ships. Still, the progression has been rapid. In 2018, less than 7% of the seafloor was mapped, and we are now at nearly 21%. This incredible progress demonstrates the power of what we can do when we come together as an international community to tackle grand challenges in our environment. Why does this matter? So this here is a close-up view that gives a sense of comparison between those two resolutions. In the background is the satellite-derived data, while that center portion is the data that's been derived from multi-beams. This difference in resolution can be the difference between a submarine grounding on an unmapped seamount, or bringing ourselves closer to shore, a ship getting stuck in a harbor. From a scientific standpoint, this level of resolution can provide invaluable information to really quite accurately predict where fisheries species, deep sea coral and sponges, and other critical habitats, critical minerals, and other resources can be found on the seafloor that will allow us to make good, sound management decisions. All right, so we've talked a little bit about mapping the ocean, but what actually lives there? The deep sea is chronically underexplored. The plot on the left here shows the drastic drop in biological observations in the deep open ocean, as recorded in the Ocean Biogeographic Information System, or OBIS. Note that this is on a log scale, so this is a really significant decline in the number of observations as you go deeper into the ocean. On the right, the graph shows the proportion of records occurring at different depth zones against the proportion of the global ocean at these depths. I'll draw your eye to the red point on the upper left corner, which represents 0 to 200 meters depth, so the near surface waters, showing just how many more biological observations we have in the surface waters compared with everything else below. Because of the lack of observations and the challenges of making them in this extreme environment, an estimated 90% of marine biodiversity remains undescribed. So one of, though certainly not the only, methods used to conduct ocean exploration and characterization is using remotely operated vehicles, or ROVs, which are typically equipped with high definition cameras. ROVs are uniquely suited to not just observe what animals are there, but also their behaviors actually in their environment, their fine scale distribution, their interactions with each other. Many scientific ROVs are also equipped with capabilities to collect samples, organisms, water, sediment, rocks, and mud. The imagery also provides a compelling method for outreach, engagement, and education about the ocean. Many of these systems have the capability to live stream in real time to anybody from 10 seconds between the deep sea floor to on your iPhone. This is an opportunity to invite everybody into the deep sea. What can ocean exploration data tell us? There's a mantra in the seafloor mapping community of map once, use many times. And this applies to all sorts of data in the ocean environment. Mapping, video surveys, and samples can inform decision-making related to renewable energy siting, distribution of critical minerals, drug discovery, populations of managed marine species, biodiversity and conservation. Ocean exploration drives innovation of new technologies and inspires people. Now that we've learned a little bit about the ocean, and I know you've learned a lot more in many of the other talks over the course of the week, let's go down there. So as you go down into the deep ocean and shine a light down there, because remember, it's really dark, what you're most likely to see at first is something like this: darkness with a constant rain of organic material slowly falling down from the surface. We call this rain of particles marine snow, and it is made up of decaying animals and excrement, various parts that are shed off of the animals. But if you travel further down, you may see something more like this. In all of the oceans, there's a deep aggregation of animals. The reason why these fishes are living at depth is to avoid predation by predators in the well-lit surface waters. These layers are commonly referred to as deep scattering layers because they can be detected by acoustic echo sounders like the systems used to measure seafloor depth. Many of the animals that comprise these layers migrate to the surface at night to feed. Through this daily migration, the greatest migration on the planet, these animals actively transport carbon from the surface into the deep, where it is more likely to be sequestered and help to mitigate climate change. There's a huge abundance and diversity of animals living in the deep water column. They have some unique properties. Many species, from fish to jellyfish, shrimp, and squid, are bioluminescent. They can produce their own light. Bioluminescence can be used for a range of communications. Bioluminescent ink can serve as a decoy when an animal is under attack. Some species have very specific bioluminescent patterns to recognize each other to find mates. Some shine light near their eyes to use as a searchlight for their prey. Many of these deep water column animals are prey themselves to economically important fisheries species like tuna and swordfish, as well as to sharks, marine mammals, and even seabirds. Yet the water column, and the deep water column in particular, remains perhaps the least explored environment on the planet, and it is thought that there is significant undiscovered biodiversity in these areas. So if you can, just for a moment, please ignore that spectacular sea cucumber. We've followed the marine debris down to the seafloor, to the abyssal plains, and you can see it raining down here in the background. The marine snow that we saw before up in the water column creates sediment, a layer of rich, organic, nutrient-heavy sediment that animals, like the spectacular cucumber, okay, you can look now, can feed on, like we see here. That sediment ultimately can be buried and thus sequestered and taken out of the atmosphere and out of our system, serving as a really important mechanism for carbon to get trapped on the seafloor and pulled out of the atmosphere. Without this so-called carbon pump, carbon dioxide levels in the atmosphere would be much higher than they are. I'll talk a little bit more about this in a bit and show some data, but I think it always really helps to actually visualize what this looks like in the environment itself. And the whole ocean is not flat. There's a lot of structure, like in the canyons that you can see in this imagery here, or in seamounts, like this chain. Areas with relief, such as the canyons and seamounts, are often well suited to harbor diverse assemblages of sponges and corals, which provide critical habitat for fisheries and many other species. There are also sparse chemosynthetic environments, like the hydrothermal vent that you can see in this video, where chemical reactions using hydrogen sulfide or methane, which would be absolutely toxic to us as humans, are used as the foundational energy source. And yet these spots are teeming with life, with mussels, crabs, shrimp, worms that are specialized with symbiotic bacteria, allowing them to thrive in these extreme environments. But as you know, and I know you've been hearing throughout this conference, the ocean is not on a great trajectory right now due to climate change, biodiversity loss, and other impacts. The ocean absorbs a quarter of anthropogenic carbon dioxide. It additionally takes up over 90% of the excess heat caused by greenhouse gas emissions. Some of the carbon is ultimately buried in seafloor sediments, as we've talked about, but that process too is vulnerable to climate change, as we'll see in a moment. And the deep sea is not immune to climate change impacts. Much of the absorption of carbon and heat takes place ultimately below 200 meters. The maps I'm showing here showed modeled changes at the deep sea floor. So these are deep sea floor predictions. Temperature in the upper left is predicted to increase. Oxygen, which is shown on the upper right, will decrease. And actually, if we were to look at this in the water column, the decreases are much more extreme, particularly in the Pacific Ocean. pH on the lower left will continue to decrease with ocean acidification. And on the bottom right, carbon flux to the seafloor, this is the marine snow that we saw before in the videos, is predicted to decrease with climate change. That's potentially creates a positive feedback loop in the climate system, where as the ocean warms, less of the carbon dioxide will get pulled out into the seafloor sediment. Biodiversity is also threatened by a number of other factors. Pollution, such as marine plastics, make their way to all parts of the ocean and have been found in the guts of many deep sea animals. Oil spills contaminate the environment from surface to seafloor. The emerging seabed mining industry has huge potential impacts on deep habitats. And overfishing and bycatch continue to be threats to many fisheries species. This map shows a score of cumulative impacts on the ocean from a range of stressors: fishing, oil and gas, pollution, heat, acidification, shipping, and more. As you can see here, all the shaded red and yellow, almost the whole global ocean is heavily impacted by human influences. So that's all a bit depressing to palate. However, there is good news. The ocean is also a powerful source of solutions to climate change. A recent scientific analysis commissioned by the High-Level Panel for Sustainable Ocean Economy investigated opportunities in ocean management that can draw down carbon, illustrated here. These methods include renewable energy, such as wind, wave, and tidal; transitioning ocean shipping to more efficient and low or zero carbon fuels; changes in ocean food demand and production, such as changes in feed source for aquaculture, and shifting market demand to sustainable fisheries species; natural ocean systems like coastal mangrove forests, salt marshes, seagrasses, and sediments already do a heavy lift in naturally storing carbon, Protecting and restoring these systems can help keep carbon out of the atmosphere. Seafloor maps and exploration will aid in siting of many of these activities, monitoring their ability to actually mitigate climate change. They're critical data to inform these ocean climate solutions. Together, the ocean-based climate solutions could provide as much as 1/5 of the greenhouse gas emission reductions that are needed to get us to the 1.5-degree warming target that was set at the Paris Agreements by 2050. Fully protected marine protected areas provide vast benefits that help to protect biodiversity and habitats. Networks of MPAs must be designed in smart ways to ensure a range of representative habitats, like some of these deep sea habitats that we've been talking about through this talk, are protected and that they are resilient to climate change. The US, through its America the Beautiful initiative, is working towards conserving 30% of land and waters by 2030. The US also recently announced the National Nature Assessment to gather data on nature, both land and ocean systems, to allow us to help monitor the changes in our natural systems. Collaboration is key, and local communities are critical to sound decision-making and science. Across the globe, low-income and marginalized people are disproportionately impacted by environmental harms, including in marine and coastal environments. The US Ocean Science and Technology community is committed to environmental justice in all of our work, committed to the fair treatment and meaningful involvement of all people, regardless of race, color, national origin, or income, with respect to the development, implementation, and enforcement of our environmental laws, regulations, and policies. Further, co-production of knowledge with tribal and indigenous communities is absolutely critical to the successful management of the ocean that benefits all of humankind. In June of 2020, the US launched a new strategy to map, explore, and characterize our waters with high-level goals to work across all of government and across sectors to map all waters of the US by 2040, to explore and characterize priority areas, to develop and operationalize new technologies to meet these goals, and to share the science and data broadly. There are a number of existing and new regional campaigns across the United States to implement this strategy. I'll highlight here today, because of our Pacific Ocean focus, the EXPRESS campaign off the US West Coast, which stands for Expanding Pacific Research and Exploration of Submerged Systems. On the international stage, the US last year joined the high-level panel for sustainable ocean economy. There are now 16 members, you can see here on this map, representing a geographically diverse set of nations. The actual panel members are heads of state, and we're seeing a lot of activity and action being led now by the ocean panel. The headline commitment of this panel is to aspire to sustainably manage 100% of ocean area under national jurisdiction, guided by sustainable ocean plans. The UN Decade of Ocean Science for Sustainable Development is now well underway, and there are a number of official projects and programs that relate specifically to ocean mapping and exploration that will facilitate collaboration on these topics. I'll highlight just a few of those here on this slide. I mentioned Seabed 2030 earlier, which has a goal of mapping the entire global ocean to a common set of standards by 2030. The Deep Ocean Observing Strategy, or DOOS, is a network of deep ocean observing, mapping, exploration, and modeling programs working together for the coming decade to characterize the physics, biogeochemistry, and biology of the deep ocean, establish a baseline to understand changes in habitats and services, provide information needed to have a healthy, predicted, resilient, and sustainably managed ocean. Challenger 150 has goals to build capacity for deep sea research globally, expand deep sea biological observations, build fundamental ecological understanding, and increase use of deep ocean knowledge. Finally, Marine Life 2030 will unite existing and emerging technologies and partners into a global, interoperable network and community of practice, advancing observation and forecasting of marine life. These represent just some of the relevant UN Decade programs. It also includes topics related to outreach and engagement on the ocean sciences, a really important part of this. So I hope you've enjoyed this tour of the ocean, and I've left you with a little bit better understanding of the importance of the ocean, in particular the deep ocean, the parts that are sometimes out of sight, out of mind, the importance of them to the pressing challenges of our time. As we look toward the upcoming Summit of the Americas, I encourage consideration and commitment to collectively tackling the challenges in our ocean, and point toward opportunities to work together to reveal and protect biodiversity and to maintain the very important carbon sequestration mechanisms in the ocean. Thank you so much. Look forward to answering some of your questions.
Thank you so much, Amanda, for that presentation. You did a really great job of taking us through sort of a virtual exploration of the ocean, giving us some context on the threats, and then exploring the ways in which the ocean can really be a powerhouse and lead on climate. Amanda, if you had to just distill it down to just sort of one or two examples, like the biggest bang for your buck, what is the role of ocean exploration in climate solutions? Like, so what are the most important types of information that we either don't have today or that we need more of, that will really move the needle on climate change? And I'm just really curious from you, like, where do we get the biggest bang from the buck? What do we need that we don't have now that's really gonna make a difference and get us closer to the, the targets we've got from the Paris Agreement?
Yeah, thank you for that, Samantha. Ocean exploration, which sometimes in terms of, the methods that we use and the kinds of measurements we're collecting, is not always distinguishable from, ocean observations and research-driven science. But I think what largely distinguishes it is the focus on the places and processes that we haven't yet studied and getting that foundational information. In the ocean, there's still a lot of places we haven't yet studied. So, prioritizing areas that we know are either experiencing extreme impacts already or are, potentially vulnerable to new industries like deep sea mining, I think is really our highest priority. And then in terms of the types of observations, I touched on this a couple of times in the talk, biodiversity, there is so much unknown biodiversity, and much of it is in these deep ocean areas. So getting that foundational knowledge of what is living where and what their life cycles are and how these organisms and communities might respond to changes, I think is absolutely critical in order to be able to make any decisions.
Great, thank you for that. And since you mentioned the biodiversity angle, and you did mention it in your presentation, and again, just now, and you talked about 30 by 30 in America the Beautiful. We heard a lot in your talk about deep ocean habitats and sort of blue water areas. I'm curious what you think the right balance is in terms of meeting, our international and our domestic 30 by 30 goals. What's the balance on these, like some of the deep ocean water habitats that you showed us in the beginning of your presentation versus coastal areas and intertidal areas and more urban coastlines? What is the right way to get at that 30 by 30 target, and what is the balance? It's a big ocean, and as you showed us in your presentation, there are just so very many different kinds of ecosystems and habitats and depths, and the human imprint is really different in various parts of the ocean as well. And so, yeah, I'd love to hear more about how you think we get to 30 by 30 and how much is that blue water versus coastal areas that might be more urbanized.
Yeah, thank you for that question. And it's a question I think about a lot, and I ask a lot of the experts about that as well, because just protecting 30% isn't doesn't necessarily protect everything, right? On land, if you only protect the desert, which might be 30% of the country, you are not protecting the full range of biodiversity. And similarly in the oceans, if you only protect abyssal plains, you aren't protecting the coastal ecosystems. So I don't have, the numbers in hand, but I do think it requires, a real consideration and analysis of what gets you to protecting the most biodiversity, right? What combination, and keeping in mind that precautionary principle that we talk about of, just because we don't know, and this often happens with the deep sea because we don't know. It's kind of easy to say, well, we don't need to worry about that, but there are really important services that it's serving, much of which we may not already have quantified. We need to make sure to get ahead of that and conserve those systems. So I think, a spread, we have a challenge in the US where we do have a lot of protected waters, but most of that is in the Central Pacific. And we need to make sure that we're getting our numbers up in the many other environments that we have in this nation. And then going beyond that to the international waters of, ensuring we're protected, our common resource, our common heritage, and working together to protect high seas.
That's great. Yeah. Thank you. Thank you so much for that answer, Amanda. I appreciate it a lot. Something else that came up in your presentation was the notion of ocean equity. And I was so grateful to see that you talked about that in your presentation. It's just so incredibly important. We're in a place now in the United States where we have Secretary Deb Haaland as the first Native American presidential cabinet member who is Secretary of the Interior. And there is this growing movement towards indigenous-led conservation and community-centered conservation. And I would just love to hear more about, again, you mentioned ocean equity in terms of decisions that we make in the ocean, and potentially even in, information gathering and ocean exploration, both in the ocean and on our coastlines. And I just would love to hear more about the role that you think local knowledge, community knowledge, indigenous and traditional knowledge can, should, will be included in the information gathering effort that's underway in our ocean right now and moving forward.
Yeah, thank you for that question. And that is something that President Biden on day one said, we are putting equity first in everything that we do. And that has, but every day we are reminded of that in our work, and have really taken that to heart. And it's made the work all that much more meaningful and exciting, because we do have, local and indigenous communities everywhere that, have the deep knowledge, have the history and background and the day-to-day experiences and the environments that we're looking at managing. And have very different perspectives. So I was learning yesterday from some Native Hawaiian folks about how their origin story is that coral polyps came from deep sea sludge and then ultimately developed into everything, and humans are kind of at the end of that chain. And thinking about how do we take stories like that, I think have a real resonance in how we should be treating our planet. It's human impacts are important, but in order for humans to benefit, we need to be putting the environment first. And so learning those stories and incorporating that into the work that we do and how we approach the science and talk about the science is absolutely critical.
Thank you for that. Yeah, I appreciate that so much. That makes a lot of sense to me. Well, we just have a couple minutes left. And so I guess I would just ask, is there anything, if there's one takeaway that you wanted folks to walk out the door with, sort of the virtual Zoom door with, after this presentation, maybe that would leave folks with a little bit of hope. What would you want folks to walk away with that's sort of inspiring going into the weekend, going into the summer, in this moment that, you know, has been really challenging for so very many people over, you know, recent years, with where we've been in a global pandemic, and, you know, we've got a lot of geopolitical issues, we've got a war, we've got, you know, oppression of historically marginalized communities, and you know, what you talked about, the ocean as a powerhouse. What sort of hope can you give us moving into the future that you want us to walk out with?
Yeah, thanks. And that is a nice setup as we're starting Ocean Month. You know, this is Ocean Month. Next week we have World Ocean Day, and there is just a phenomenal lineup of you know, here in the U.S. domestic activities, but perhaps even more importantly on the international front, international activities that are being announced over the coming month. We have the UN Ocean Conference coming up at the end of the month, where, you know, the whole world will be coming together to work together to tackle these challenges. And you know, someone recently said, you know, it's not just Ocean Month. This is the summer of ocean action, because there's so much happening right now in the ocean space and so much energy. And you know, I'm being approached by people who are, you know, in traditional fields that are traditionally so far outside of ocean science, looking to connect their work and bring oceans into their work and help solve these problems in the oceans. I think we're, you know, I'm hopeful that we're really in a place where this collective action will really help and make these changes, and that we're all work together as an international community to, you know, make the world a better place.
That's great. Thank you so much, Amanda, for being here today. And it's been an honor to have a chance to talk to you a little bit about some of these issues.